Hey, good morning, everyone. Today we will begin chapter 3, diodes. Okay. That's the first of our semiconductor device. And we'll spend, I would estimate, at least 2 whole weeks on this, if not more. All right, so let's bring up the class notebook. Okay, so in chapters 1 and 2, in chapter 2 especially, we just saw about, let's see, a little bit of the electrostatics of a p-type semiconductor and a n-type semiconductor. Now we will see what happens when we bring both of them together. So this here is a illustration of a p-n junction semiconductor, where you bring a p-type semiconductor and an n-type semiconductor in contact with each other. Now, this is a illustration. This is what we kind of use when we're instructing students. But when we are actually fabricating, if you recall from the silicon wafers last time, this is not actually how it happens, right? It's not as if we create two separate devices and then bring them together with some sort of glue. That's not how it happens. We would have like a p-type material. This would be a top view. And then we would create a n-type material inside it. This is typical fabrication. P-type and then create n-type in there, or it would be n-type and then create a p-type junction in there. But for teaching purposes, this is the model that has been consistently used. Again, for research, for teaching, for any other purpose, we use these kind of models. So we have a p-type semiconductor, we have an n-type semiconductor. They are now in close proximity. They're actually in contact. Let's see what happens when you bring these two together. The first thing is the contact region is the junction. You have two different semiconductors meeting, so it's known as the metallurgical junction, or simply known as the junction. Okay, simply known as the junction. All right, simply known as the junction. Now, when we create semiconductor devices, they are at the micro scale. Since they are at the micro scale, we cannot directly connect macro scale wires to it, like the real life wires that we use. They are far larger and bigger in size to actually make contact to these small, tiny microchips. And so we have some sort of metal, typical a metal pad or a contact pad. Contact pad to act as the interface between the semiconductor device and the outside world. Okay. Now, of course, it's not just about size, it's about material properties. So the pads are made out of a conducting material such as aluminum, copper, gold. There are gold bond pads on the IC packaging. There are aluminum traces that are running inside the IC. There is also copper that is used, but by far the most preferred metal for for silicon is aluminum. Okay, so typically metal of choice is aluminum. There's copper also used, as well as gold. Okay, so p-type material, we have an excess of holes. And so here, the hole concentration is larger. It's from the externally implanted impurity dopant. The intrinsic material would be the background concentration. And so if it's a p-type material, it's acceptor atoms, right? They accept the electrons from the intrinsic semiconductor, the intrinsic silicon, and that gives rise to an extra hole particle. And so the majority carriers are the acceptor atoms. Sorry, the positively charged holes, meaning there's a lot of acceptor atoms present in a p-type material. And the opposite for the n-type material, you have a lot of electrons. And so you have a lot of donor atoms. So the total number of electrons from the donor atoms. The minority carriers on both sides would be holes and electrons, reverse, right? In a p-type material, you have holes as the majority carriers and electrons as the minority carriers. In a n-type material, we have electrons as the majority carriers and holes as the minority carriers. The symbol of the diode is shown here. It's like a arrowhead pointing towards the cathode. It basically points towards the direction of the flow of the current. Right, it goes from anode to cathode. And if you remember the first day of class, these names come from the vacuum tube diodes, 2 electrodes. The electrodes were known as cathode and anode. And when they created the solid state version to replicate a vacuum tube diode, the names carried over, and we still refer to them as the anode and the cathode. Okay, so cathode is also marked with this straight line. Okay, so it's a triangle, it's an arrowhead pointing towards the cathode, and the cathode is also marked with a straight line. On real life diodes, which you may have already seen in your lab kits, it's marked with a silver band or a gray band. So if it's a plastic epoxy packaging, it would be a dark packaging with a gray or silver or white band running around it. That indicates the cathode. And if it's a transparent packaging, it would be some sort of, I don't know, some different color or maybe a black band running around one end. And that band indicates the cathode of the diode. Okay. Practically, if we have a multimeter and we have a diode, you can look at the multimeter terminals, and there you could see this exact same symbol. And most multimeters have these, even the cheap handheld ones. And what they indicate is you could test the continuity or the working of a diode by using those terminals. So in one direction, the diode would conduct, it would beep. If you connect it in the opposite direction, if it's not working, it shouldn't. Okay. All right, so what is happening at that junction when we bring it into close contact? Here, this basically, the illustration shows you a graph of X and Y axis, but realistically speaking, it's actually in both directions. Okay, this is going into, this is the junction, right? This is the junction right here. And the arrowheads are actually pointing into the N-type material. So you're going deep into the N-type material. And this way you're going into the P-type material. Physically, you're going into the N-type and the P-type material. Now, P-type material, of course, the number of holes are higher than the number of electrons. Again, remember, N is used to indicate the number of electrons. P is used to indicate the number of holes. So PP means it's the number of holes in the P-type material. Okay, the subscript P indicates the type of the semiconductor. Again, the subscript indicates the type of the semiconductor. And the P and N, of course, basically, so PP indicates the number of holes in the P-type semiconductor, and NP indicates the number of electrons in the p-type semiconductor. And again, you can see we illustrate this is basically the number of holes and electrons, charge carriers, or carriers for short. Okay. 10 raised to 17 atoms per centimeter cube. Number of electrons is 10 raised to 3, 10,000 atoms per centimeter cube. Intrinsic versus extrinsic. And the same thing on the N side. Subscript of N indicates it's a N-type semiconductor. And then Nn is basically the number of electrons that are present in the N-type semiconductor. And then Pn indicates the number of holes in the N-type semiconductor. Okay. So let's take a 10-second pause. Let me know if you have any questions. These are the majority carriers. These are the minority. Oh, yes. Sorry.
Seems like there's more holes generally. Like, what's the reason for that?
So the question being asked is, why is the hole concentration larger than the electron concentration? Is not in general, it's basically the device that we want to create. The background, I mean, this is an implanted impurity, right? So the hole concentration here is chosen by the engineer depending on what kind of device we want to make. If I was making, so for example, when I used to teach the clean room class at Louisville, we used to create resistors so I was creating a MEMS device. So we are creating piezo resistors in silicon. Piezo resistivity is one of the properties of silicon materials. So we want to create resistors. Now, to create those resistors, we need specific resistivity. And so the implant the implant of the atoms in the silicon, the dosage comes from, well, whatever resistance we want. So there are calculations we perform to determine what kind of implant would be needed to create that specific resistance. And so in general, it's not a given that the holes would always be higher than the electrons. It is depending on our application and need. In this illustration, it shows the holes are higher than the electrons. Maybe as a way to like balance out because the hole mobility is less than the electron mobility. And so that makes a difference if you want to have like completely balanced device. But again, that's not a given. This is a random example here. Any other questions? You imitating me? So what happens when we have a imbalance of electrons and holes on either side of the junction? Well, on the left here, what we are showing is we are showing an expanded view, of this junction, right? We are only focused in that narrow width. Oh, sorry. Like in this narrow width right here. Okay. So from the left, we know that the hole concentration is higher all the way until the junction meets, and then of course it crosses over. All it is showing is the hole concentration is higher in the p-type and lower on the n-type. Now, if we expand the junction, we see that a diffusion effect takes place, right? We talked about this in chapter 2. When you have a concentration gradient, where the number of carriers is higher in one area and lower in the other area, there is a diffusion current that takes place. The carriers try to diffuse through the material in an attempt to balance out the concentration. So when you bring a p and n-type material together, there's an imbalance of concentration of these charge carriers. There's an excess of holes in the p-type, excess of electrons on the n-type. So if it's an excess of holes on this side, means a higher concentration of holes on the P side and lower concentration of holes on the N side, these holes right here try to diffuse through the junction, try to cross over the other side in an attempt to create a uniform concentration. Okay, uniform concentration of holes throughout the semiconductor, which doesn't, of course, happen. And we'll see that in the next couple of slides. But that is what is happening. You have a imbalance of concentration, and so the holes are diffusing towards the N side. This is the P side. This is the N side. The same, yes.
But we can kind of like cross over that little gap.
Yes. So the question being asked is, when we refer to the phenomenon of diffusion, is it actually crossing the gap? There actually is no gap. It's a junction, but it is crossing over the border. It does cross over the border. So we'll look at what actually happens. So it crosses the border, tries to go over to the other side. Same thing happens with the electrons. Electron concentration is higher in the N side, and because the electron concentration on the P side is lower, the electrons are now trying to diffuse through the border, through the junction. Let's be more technically accurate. It tries to cross over the junction and goes over to the other side. So holes are diffusing from the P side to the N side, and electrons are diffusing from the N side to the P side. They're crossing the junction. Okay, this is the phenomena that we referred to in chapter 2, diffusion. That gives rise to diffusion currents. Again, there is no externally applied field. There's no external energy source. It is simply diffusion. Okay, so the charge carriers diffuse through the junction. So charge carriers diffuse through the junction. To create a uniform concentration. Okay, the charge carriers are diffusing from both sides. Holes from the P type, electrons from the N type. So now what happens when they're actually leaving? If you think back to chapter 2, you have extrinsic semiconductor, meaning you have external impurity dopants that are coming in, right? If it's a column 5 compound, N-type material, column 5 compound has a donor atom. Electron is free to move about. But now that electron is actually leaving that localized region and going across the junction. It leaves behind the ionized atom that has an extra positive charge. Okay, and so this is what happens. In the N-type material, electrons are moving in this direction, and they're actually crossing the junction, this direction, and holes are crossing the junction in this direction. So again, electrons are available because we have column 5 elements, sorry, not compound, column 5 elements, meaning donor atoms. 5 protons in there, 1 electron running free. That electron has now crossed the junction over to the other side, leaves behind an ionized atom with a positive charge. And hence we see these positive charge ions right there. which is right here. Okay, ionized donor atoms. And on the P side, the same thing happens. We have acceptor atoms, column 3 elements. Holes are now crossing over the junction. Holes cross over the junction, leaves behind acceptor atoms or ionized acceptor atoms. And so we have one negative charge for each hole that crosses over that junction. So far, so good. Okay. And what that does is it creates a region in the middle right there that is devoid of charge carriers. Because now the charge carriers, the electrons on one side, sorry, electrons on this side and the holes on this side have crossed over, leaving this side of the p-type material empty and this side of the n-type material empty. And so it's completely depleted of charge carriers. So let me write it here. So depleted of carriers. No electrons and no holes. All we have left is ionized acceptor and ionized donor atoms. Okay, and that region is known as the space charge region, space charge layer. More commonly, we refer to it as the depletion region because it is depleted of all charges. Okay, so depletion region. This is by far the most common and accepted usage of this term, depletion region, because it is depleted of all charges. Yes.
Why does it not happen at the largest, like only small?
That's coming up on the next slide. Yeah. So the question being asked is, wouldn't all the holes and electrons just flow through until the entire P and N type semiconductor is uniform concentration? And that is what we would have expected. But I'm just speculating here, like when they did it, when they created this P and N type material, P and N junction material, they were expecting to see something like that, but it didn't happen. So then they postulated a theory that there would be a competing mechanism that opposed the diffusion current, which is coming up on the next slide. Okay. So the point being made, and it's a very valid point, is that if there is a diffusion gradient, if there's a concentration gradient, wouldn't all of the holes and electrons flow through until the concentration was uniform throughout the device, right? That is what you would expect it to happen, but that's not what happened. And so theory was postulated that there would be a competing mechanism that opposed the diffusion of the carriers. Okay. Okay. So what happens is you have diffusion currents, and I to point this out right here. Yep, FX. So diffusion currents flowing through because of the diffusion effect of the charge carriers will cause localized charge density variations right around the junction. So there are charge density variations, right? Electrons and holes are going through. There's variations in the charge density. And that gives rise to an electric field. And that is noted by this E of X right here. Okay. That gives rise to an electric field. And that electric field within that junction gives rise to the second phenomena of drift. Again, referring back to chapter 2, we had drift currents and diffusion currents. Drift currents are the movement of charge carriers in response to an applied electric field. Here, we are not applying any electric field. There is no external field. It is internal due to the movement of these charge carriers. Okay. So it is built in. It is kind of built in. And that is also the term that we use for the voltage that develops. So we have diffusion currents due to the concentration, carrier concentration gradients. carrier concentration gradient. That gives rise to localized variations in the charge density. These localized variations give rise to the electric field. And that electric field acting on the charge carriers will result in a drift current. And because it's in the opposite direction, that drift current cancels out, well, doesn't cancel out the diffusion actually. It balances out the diffusion and stops the charge carriers from moving further into the P and N type material. So the total, once it reaches equilibrium, the total current after equilibrium is 0. The width of that junction depends on the material. So every semiconductor has a different width of the depletion layer. So this results in total current being equal to 0. Yes. Sorry, carrier concentration. Again, anytime anyone can't read what I write, please feel free to ask. Sometimes I'm in a rush and my chicken scratch would be worse than a doctor's prescription. Okay. All right. So let's look at a couple of, not a couple of, three. Just so charge density. Okay. For the charge density, we know that from previous experiments and research, we know that when a P and N type material are together, the overall current that is flowing without any external energy source is 0. Okay, that means that the overall charge density must be equal. Okay, so that's what we see here. This is going into the N type material, and this is going into the P type material. Okay, physical distance into the N type and the P type material. Depending on the concentration of the atoms, the total charges are balanced out by the number of acceptor atoms and the number of donor atoms. Okay, it's a phenomenon that takes place specifically at the junction. And so we can write the total charge Q and A times XP, the depth in the P-type material, would be balanced out by the total charges on the other side. Basically, it will keep going into the P and N type materials until the charge is balanced out. Okay, so even if NA and ND are different, the XN and XP, how deep they're going into the material, would change until it balances out. And then, of course, that gives rise to the electric field. The electric field, of course, will also not be uniform. And then it reaches a max level. We call that E max. And then integral of the electric field gives us the voltage or the potential that develops across that junction. Okay, and that is known as phi j, the junction potential. It's also known as sometimes the built-in junction potential. It's the built-in junction potential because we are not doing anything, no external energy source. We're not doing anything special beyond simply creating the P and N type semiconductor in proximity or in contact or in proximity. All right, 10-second pause. Let me know if you have any questions. Any questions? Yeah.
To actually create the
At what point, as in what point in terms of time or physical distance? That depends on the concentration. So the question being asked is, I think, where is Xn and where is Xp located, correct? And that depends on the material, the intrinsic background concentration, plus the dosage of our implant. So everything is a variable, and the requirements of the application decide, what we need. So there are tons of well, let me not put it that. There are equations and qualitative and that describe the qualitative and quantitative explanations for how deep it is. The junction depth, meaning how deep the junction is into the P and N type material, that is also a important factor, but we don't look at it here. Okay. So there are a couple of equations. Phi j, the junction built-in potential, is given by Vt log of NA/ND over Ni square. Ni square again describes the intrinsic concentration of the carriers. Na and Nd are the doped acceptor and donor atoms. And Vt, of course, is the thermal voltage. WD0 is basically the width of the depletion region. Okay, WD0. So again, this is a lowercase w. Okay. We're only limited to 26 letters. So a lot of the letters are used for multiple quantities. So in this case, WD0 stands for the width of the depletion region. And so how far into the material the depletion region will extend. And so, of course, that is given by the distance into the P-type material and the distance into the N-type material. Xn and Xp are basically the distance into how far the junction extends, or not the junction, how far the depletion region extends into each P and N type material. P and N. N and P type material. Yes. Oh, yes, that's a type right here. 1 over, I'll get that fixed. So 1 over Na plus 1 over Nd times phi j. Epsilon s is the permittivity of silicon. Remember from the capacitance equations? Oh, and it's given by epsilon r, the relative permittivity of silicon with respect to free space, and then epsilon 0, which is the permittivity of free space. And epsilon r has a value of, see, 11.7. Yeah, 11.7. That's for silicon, material property of silicon. And of course, Q is charge. Q is the standard unit charge. And phi j is the built-in junction potential. That again is a function of the number of atoms that are implanted. So Na and D in I square. All right. Okay. All right. So let's look at a straightforward example. If you have calculators, I would suggest you take them out now. You're asked to calculate the built-in potential in the depletion region width for a silicon diode. Then we're asked to calculate Xn, Xp, and Emax. Okay. So phi j has to calculate phi j, excuse me, WD0, then the distance, the junction, not the junction, the region extends into the N-type material, the distance, the junction, and extends, the region extends into the P-type material, and the energy, sorry, not energy, the electric field, Emax. Now, standard equations, pretty much everything is given. Everything is a constant, and there's only one unknown quantity. So it's simply plug and solve. So if we begin, Na and Nd are given to us. Take the equation. And plug in the values. So first calculate phi j, because phi j is needed for WD0. Excuse me. Ni for silicon is 10 raised to 10 atoms per centimeter cube. Calculate that while it takes a short break. No, thermal voltage is something that you will see again and again and again throughout semiconductor devices. And for silicon, standard thermal voltage, well, actually for any semiconductor, thermal voltage would be 25 millivolts. So phi j requires 4 quantities. You simple plug and solve Vt log of Na and D over Ni square. Yes.
Professor, what exactly is?
That is the voltage that arises due to temperature because of the differences between the charge carriers. It is. It's a function of temperature. So where did it go? Oh, I thought I had it here, but Vt is Kt over Q. First, I'm mixing it up. Hold on. All right, any values for phi j? No one has a calculation yet? Did you take ni square or did you take ni? That is correct. .979. Then we take that and plug it into the equation for WD0, depletion region width. Yeah, we have to take every unit prefix into account. So built-in potential voltage. Uh-huh. Just volts. Yep. 0.979 volts. That's a epsilon 0 is 8.85 into 10 raised to, was it 13, 14? 14 farads per meter. Epsilon R was 11.7. What else do we need in that equation? Na and Nd is given to us. Q is the standard charge. So 1.6 into 10 raised to minus 31. There you go. No, wouldn't, because you have Na and Nd, which are like 10 raised to like 17 and 20 in the denominator. So be very, very small. Which one? Oh, minus 14. Minus 14. Permittivity of free space. 8.85 into 10 raised to minus 14. Anyone? No answers? 1.126 times 10 raised to minus 5. It's 10 raised to minus 4, I think. And it would still be not 10 raised to minus 5. It'd be, the answer would be in microns. So 10 raised to minus 10 if we convert everything correctly. The answer would be 1.1 something into 10 raised to minus 10. Okay, we're almost at the end. So you give up? Oh, this is for sure going on the quiz on Monday. Similar, similar question. Okay, now the example is there in the book. Let me just write out the answers. So for WD0, the answer is 0.113 microns. So that would be 0.113 into 10 raised to minus 6 meters, or 113 into 10 raised to minus 9. Okay, that is what you got. Oh, 10 raised to minus 5. Okay, that is correct then. Yeah. Anyone else? Only one student out of 20? All right. Okay. WD0 is also the depletion combined of xn and xp. So we can find xn and xp by using those equations. So xn can be determined as, let's see, where did my equations go? Oh, yeah. Xn is WD0 divided by 1 plus ND over NA, and XP is WD0 divided by 1 plus NA over ND. So please practice, arrive at the right answer. 113 micron. Okay, and Emax is 2 pi j divided by WD0. It's the first two examples in the book. So perform your calculations. Again, simple plug and solve. The reason I wanted to do this little in-class exercise is, again, for the same reason. It's like students to take into account the unit prefix and try to arrive at the right answers, which is something you'll be doing as an engineer over and over again for the rest of your career. So unless you like doing that, then you're in the wrong field. All engineers do have to do that, right? So, all right. We'll end class here today. We'll pick up here again next on Friday. Yes, so I'm gonna post that's a good point you brought up. Sorry, I was gonna announce. So there'll be a short homework assignment. Reading as always, whether it's a reading assignment or not, students should, read the corresponding chapter from the book, and then I'll have a short homework assignments to prepare for this. And we'll cover a material on Friday also. So there might be two homework assignments. Yeah. One 1.126 times 10 raised to minus 5. Yeah. Yeah. So it'll be 0.11 micron. Yep. Hey, all the best with your career fairs.